Lab 5, the world's highest skydive. The purpose of this lab was to model the motion of Felix Baumgartner's jump from the stratosphere and compare it to the experimental jump. For this, I used Newton's second law and the momentum principle, Newton's law of universal gravitation, and Newton's third law, and the motion that I modeled was similar to the experimental motion undertaken by Felix, with a few differences. These are the equations that I used: Newton's second law and the momentum principle, the law of reciprocity, so Newton's third law, and Newton's law of universal gravitation. Some assumptions that I made: I assumed that gravity and drag were the only forces in action here, and I made an assumption that the parachute experiences more drag than a human alone. I estimated the change in area to be a ratio between the area of the parachute and the area of Felix's body alone. Because of the nature of the experiment, I used the starter code from Lab 2 to model this motion. The system here is Felix, his suit, and the parachute, and the Earth and space in this case are in the surroundings. Felix had a mass of 118 kilograms, and he exited the capsule at 39,000 meters above the surface of the Earth. He had no initial velocity. So the experiment, in 2012, Felix Baumgartner jumped out of a capsule 39,000 meters above the surface of the Earth, and he fell in free fall for 260 seconds before he opened a parachute and glided to the surface of the Earth. He reached a velocity of 377 meters per second, exceeding the speed of sound, and the first person or object to do that without an engine. So in the code, I created two while loops, one that included the drag force on his body and the gravitational force, and one that occurred after he opened the parachute that included the force of gravity, the force of drag on his body, and the force of drag on the parachute, including a ratio of the area of the parachute and the area of his body. Then I modified the initial mass, or the system mass, and I changed the position to be his initial position of 39,000 meters above the surface of the Earth. I changed delta t, and I modified the drag coefficient based on experimental manipulation. These are the graphs produced. Felix's velocity increases until it reaches about negative 400 meters per second, and until the point where he opens the parachute, and his velocity decreases significantly after that, and the position also changes at a significant rate. In this case, his velocity or position went below zero, which is an error. So some similarities and differences. Felix fell at a rate of negative 377 meters per second until he opened the parachute, but in the velocity graph of my code, by the time he opens the parachute, his velocity is almost negative 400 meters per second. This might be due to a difference in the experimental drag force compared to the one produced by the model, but in both the model and the experiment, Felix is close to reaching a terminal velocity before he opens the parachute, reducing his velocity considerably, almost to zero, as seen here. There may be errors due to incorrect calculations of the area ratio of the parachute and his body, and/or of the drag coefficient. So what does it mean that his velocity plateaued before it slowed down? So Felix's velocity plateaued about 100 seconds before he opened the parachute. In this case, it means that he reached a terminal velocity, faster than the speed of sound, at which the force of gravity and drag on his body were equal, causing the net force to be zero and his velocity to remain constant until he pulled the parachute open, after which he started slowing down. And what if a jumper had been hit by shrapnel? There are lots of asteroids and other astronomical bodies that could potentially contact a jumper in space. So Felix wasn't high enough to hit any astronomical objects, but this idea comes from another video also linked in the description, along with the video of Felix's actual jump, about the impact force of such shrapnel. If the shrapnel were moving at a rate of 7,777 meters per second and had a mass of 3.9 times 10 raised to 15 kilograms, after a collision it would impart 1.18 times 10 raised to 23 joules of energy to the jumper. Not considering the impact force, we'll just consider his temperature. For a person of Felix's mass, who we'll assume has the specific heat of water, being mostly composed of water, his body temperature would be raised by about 2.39 times 10 raised to 17 degrees Kelvin, or Celsius. Needless to say, he probably wouldn't survive the collision. But it's an interesting experiment.